probably this is a very stupid question, but I'm going to ask anyway. Because, I understand that now instead of having just one number like in the standard table, you have a distribution or something like that. But I know that you have to change your way of thinking to use statistics with the symbolic data analysis. But for example, I want to correlate the distribution of age by the distribution of income or something like that. How do I do that? Because I know that there is the standard table, you have your Pearson correlation or whatever, but
you are asking the question at the level of at the bottom level of the ground level,
how do I correlate that distribution?
Yes. How, for instance, I correlate the gap 1 and gap 2. This is the question? How to correlate this kind of variables?
Exactly.
Yes. So there are many ways to do that. I will speak about that later, but I can explain it quickly. What you can do is to take, for instance, in this case of 2 variables, but you can extend it to other variables. You create new variables by taking here and here the categories which are the most correlated. So I create a new variable where I will have, for instance, the category 2 and the category 3. And then another variable with category 1 and category 2. So I group together the variables in such a way I have columns of numerical values. And then the question is to maximize the correlation of these 2 by 2 variables. I will silence that, but I will explain it. I can explain that now if you want, but if you see the idea, yes. But for sure, many method has been developed also to do regression, canonical analysis, so always this problem appear. And so there's a fight now between people, because some make the assumption, possible if you have intervals, of uniformity, because you know nothing about the intervals, and the other works directly on the values that you have. Because if you have interval, you have the mean, the max. Another interval, you have the mean and the max. So you can, if you have 10 intervals, you have 2 power n, 2 power 10 possibility. If you have 2 intervals, you have 4 possibilities. You have 10 intervals, you have 2 power 10 possibilities. So this is the method of submit. In that case, you calculate the correlation on these things. You have a big data table with 2 power 10 rows. And so you apply PCA on that, and then the submit associated to the same class, you constitute a vertices, and then you adjust to get the rectangle which contains that, or the convex rule which contains that. And here also there is another fight, because some people prefer rectangles, others prefer the convex rule which contains the points. So, also other people prefer to take the centers, the center method. They take the center of the intervals, they make PCA, and then they project the other points on the PCA. Also for regression, for canonical analysis, for discriminant analysis, all these things has been developed like that. But much remains to be done. For instance, I think this last one. Any other question? Yes.
My question was exactly the same, but I have I don't understand how do you compare between variables with different kind of, for example, histograms with intervals or something like that.
How can I compare two columns like that?
Yeah.
Sorry?
For example, one is internal and the other is external.
Yes.
How do you define the distance between two variables?
We can imagine many ways to do that. For example, a simple way to do that is to replace this variable of intervals by the mean and the max. So you have two variables. The other variable, you have four categories, you have four values. So in that case, you have a standard data table. On that you can build a PCL. This is one way. But there are much more sophisticated ways. As I said before, you can use the fact that you have many possible combinations. You can take the mean and the first frequency and the first variable, second frequency of the second variable, and put all these rows and then aggregate all these things. But there are many papers you can go to them. But intuitively, for instance, to calculate the correlation between two histogram variables, we can make the sum of the correlation of the categories. So you work. This also there's a fight here at that level because some people want to compare just the frequencies, and other people want to compare the frequencies but taking care of the value of the interval. You see? Much remains to be think about that.
No, just to clarify what PCA is, because a principal component analysis is because we use it in Spanish, análisis de componentes principales.
In fact, what we call PCA, you have a standard data table. You have, for instance, players of a football team, and you have the age, weight, and so on. And this, if you have 10 variables, standard variables, numerical variables, and you have 100 players, for instance, this is a cloud. You have each point, each player is a point in the cloud of the 10 variables. And the age, weight, salary, and what you want. So you have 100 players. You can put them in a cloud in a space of 10 numerical variables. Now, I can't make a, no. So imagine your cloud. Suppose your cloud is like that, and you want to represent this cloud in 2 dimensions because you want to see what happened with this cloud. So principal component analysis aim is to find an axis which will take the inertia, the best inertia of your cloud. If the cloud is like that, the axis will be like that. The best axis will be like that. If it's like that. The worst axis will be like that, because if you project on the orthogonal axis, you will project all the points in something you can see nothing. What we want is to find the axis which project as best as possible, as clear as possible your cloud. And then you look for the second axis. And in fact, mathematically, this means that you have to calculate the eigenvalues of a correlation matrix.
Yeah, I mean, some of the students, if they are involved here, they know about principal components.
Yes, yes.
But some of the lower students,
Okay.
they don't know that because they still haven't seen that.
So, as I said, if you understand what is the principal component analysis, aim is just to visualize a complex cloud of data with many variables, and so also it allows you to summarize the data. Instead of having 100 variables, you have only 10 variables because they are the same first axes. And so what we have done is to extend these things to the case of complex data. Because this is one data table. If you have many data tables, you have to aggregate that, and you need to symbolic data. In fact, standard data is one cell of the symbolic data table. And in one cell of the symbolic data table, you can do inference parameters, load, find rows, find parameters, and so on. But I will speak about that also later. Another question, no? So I will start. Now we have two parts. One part is an initial application, and then direction of research. So this is an example of tables that you had. SNCF is a railroad company in France. And so this is a problem for each row represents a train going on the bridge at a given temperature. And each cell contains until 800,000 values. So this is a signal of the sensor 1, sensor 2, sensor 3, on the bridge. They put sensors on different places of the bridge. And the question was to know when the bridge had the problem, they repair it, and they want to see if the signal will be good after. So they want to see, it's a way to verify that what they have done is good or not. So we had such data, which is a huge set of data table because 800,000 values in each cell. And so we could use maybe wavelets, or just the most simple way is just to project this value on the y, this x-axis, and the y-axis. And then you have many points, and you can build an histogram on that, on the solution. So each cell is transformed in an histogram from projection of wavelets, and then we obtain a symbolic data table, and so we could answer the question. This is another example. The units were the speed. It was, maybe you remember the time where pigs gave illness. Not remember the name of the illness. So we had pigs in farms, but the people were not interested by the study of the pigs. They were interested by the study of the farms. But each farm had pigs. So each farm was a class of pigs. And we had 19 variables here. And then we have transformed each farm by relation of the variable of pigs, and we obtain a symbolic data table. And we could add also the farm's variable. See, when you go, this is important to understand that this is possible in our software. When you build a symbolic data table from the initial variable, when you go at the level of the concept of the classes, this is the farms, you can add the variable of farms. So here you have 19 variables, then you have 19 variables, plus maybe other, but also plus all the variables which concern the farms. So you have much more variables. For instance, if we go back to the football teams, you can aggregate for each team the variables of each team to have the symbolic description of the team, but also at the level of the team, you have also other variables that you can add. The manager of the team, where the team is the founder of the team, the vision of the team, and so on, which are not at the level of players. So this is the concatenation process. So from numerical description of pills to symbolic description of forms, numerical variable and category variable are transformed in bar charts of the frequency based on 30 animals or interval value variables. So we get interval value variables or bar charts. And this was the result. So we had here the concepts of the forms or groups, classes, and here you have the variables. And you can see, you could see quickly what is the difference between the different forms, what is the variable to distinguish the best of different forms. And also if you have the kind of index of the pigs, you could have it here in each form. This is a nuclear power plant example. The question was, I spoke about it just before, find correlations between three-terminal data tables of different observation units and different variables. So, an inspection machine, this is an inspection machine, can detect cracks and can detect grid, can build a grid, and so you have a table 1 where cracks are declared by cracks by description, so the lines, the thickness of the crack, the color of the cracks, and so on. The second table was about gap deviation of different periods compared to the initial model position. So at the beginning, the tower has a position, and with the time, the tower changes position. So what is it's important to know this is not like a Pisa tower. So they look at that very precisely. And you have also a grid, and you can see what is the oppression from the ground of the grid. All this data are transformed in one symbolic data table, where the classes are the towers, on this table, then SDR can be applied. So now I can explain once better. Aggregation means that for each variable of crack here, I can build a distribution or an interval or so on, a list of values. Correlation the same. So I obtain one row here, and the second total the same, I obtain a row. And then I get a symbolic data table on which I can apply symbolic data analysis. Also, we can do towers on PCR first axis. So we can each tower for one variable, we choose one variable, and we have here the representation of each tower for this variable. The P chart of this variable for one given variable. And also, you can ask for clusters, and the cluster will give you directly the cluster on the PCA plane. These are the clusters obtained automatically by the system. For sure, nothing is by hand here, all is automatic. This software is called Netseer. Also, you can calculate the correlation between the singular variables, but also between the standard variables. As I said before, if you have a single data table like that, maybe another one, yes, this one, oh, sorry. Oh. The PCA, the correlation circle, gives you the correlation of the bins. What I call a bin is this categories. So you can get the correlation between the bins, which are numerous, but also you can have the correlation between the single variables themselves. And it can be shown that the single variables themselves can be projected in the correlation circle, but they are out of the correlation circle, they are in the hypercube. So you can see here that you have some variables which are symbolic variables which are out of the circle. Now another example is an example in text mining, about text mining. We had here documents. We had how many documents? We had 31,000 documents and 2,000 words. And then this says in the data table we have 2,800,000 rows. Why? Because each document is repeated here for each word. So we have document 1 has the word bonjour, document 1 has the word oui, monsieur, and so on. So we had this number of rows and 2 columns only. And the question was, people of call, and they asked us to say, tell us what about they are speaking. What are the main questions? So we apply cluster, which is a symbolic data method which gives you clusters. So we start with the first data table of this number of rows. We apply, we aggregate each document, all the word of each document, and we obtain a kind of histogram here, which also, this histogram had 2,258 categories. Very big histogram here. Very big marchand, I want to say. Having this set of documents and this description, we apply a clustering technique and we reduce the 31,000 documents to just 70. So we get 70 clusters. So instead of having 31,000 documents, rows, here we had only 70 rows. But the same number of categories for the histograms here, the same. Now, we reverse the question, and for each word, we describe it by the TF-PDF is some kind of TF-PDF for people who work on text mining. It's a kind of frequency, let's say. So we have here the 70 cluster of documents as columns, 70, and here we have the 2,000 words as the rows. And we apply a clustering technique on the rows and the words, and we obtain 80 cluster of words, 70 cluster of documents, and the data table of 80 rows and 70 categories here. So each of the rows, each of the cluster of words was called a theme, each cluster of words had a meaning. So we call this a theme. And then we obtain here finally a class of documents, and then the theme, the class of words. Échéancier, dépannage, technical words, flavors, and time to pay, this kind of paying, this kind of cluster of words we had. And finally, we produce this kind of result for the user. You could see here all the clusters. Here we had 1, 2, 3, 4, 5, 6, let's say 6 clusters. And each cluster had a meaning, and they give you what people are speaking on. For instance, we had one cluster was about failures, one about budget, about address, address, about vacation, and so on. So the graphical representation of things document classes by p-chart and the bar chart description. So for each document you can click and have this thing, so you know what are the most frequent words or documents. We have also a social network which is obtained in the PCA by this network is based on the similarity. The layers of similarity are presented here. Also you can add annotation, and you can move and zoom this software, this PCA. Another application is surveillance security. This is more official statistics, let's say. You had a sample of people of 3 regions, much more, but in fact here I want to summarize the thing. One region was VEX, second was VAL, the play, 3 regions. And here you had the gender, and the security and the finality. So you ask people, the gender for sure, but question of security was, what is the priority in order to fight against insecurity? What is the priority? The best is to fight against unemployment. The best is to fight against genuine delinquency, or the best is to fight against drug addicts. In each region, we had the histogram of answer of the people. And so, gender, security, death penalty are Bayesian values in case of symbolic data. And so we could apply symbolic data analysis on this data table. And so here I come back to the question, because we had such data, this data table with the values of the frequencies, and we have transformed this data table in what we call metabean latent variables. In metabean latent variables, we aggregate, we create new variables by taking one bean in each variable. For instance, here we create male, juvenile delinquency, and answer yes. And here, for the second variable, we take woman, if I don't know what it means, and no. And this, we take these 3 variables, no, D and U. So the question was to build this data table in order to maximize the correlation. And then in that table, you cover much information, more than you. So there's a paper on that if you're interested. Now, so, yes.
Okay, good time is.
So, now we will speak about open direction of research. So I will say model of models, law of parameters of laws, rules of vector of laws, copulas needed, 4 general conversion theorem, optimization in unsupervised learning by lower parameter clustering. So I recall what I said before about building symbolic data by improving quality of the symbolic data table. So So what we can, how can we change the simulated table? We can change it by changing the variables that you have chosen. As I told you before, when you have a class, you can say, oh, this class is a beautiful thing. It is an object. As an object, I can describe it by many things, by many variables. A class is considered as an object by itself. In fact, all symbolic data analysis is based on this idea that you have objects and description of the objects. Often in statistics, people mix everything and they consider objects, the units, as variable also. But no, I think if you want to understand symbolic data analysis, you have to keep well in mind that objects is a set of something, variables is a set of another thing. If you read Aristotle, in the Organon, there is a book of Aristotle called Le Livre des Catégories, about the category. He says very clearly that objects and variables are not symmetric. There is no symmetry between variables and objects. You can say that the table is red, but you can't say that red is a table. So you have to keep in mind that you have, at the beginning, you have statistical units which are objects of the lowest level, and then you have classes which are objects of higher level. At the lower level, you have, for instance, 10 variables which describe your basic units, players of a football team. At the higher level, you have classes, teams of players, described by other variable. You can use the same variable to build symbolic data, the same variable as the variable which describes the players, but you can also add other variables because the class is a beautiful object. You can describe how much variables that you wish. And so the question of this slide is how to, among all the possibilities that you have, how will we restrict to the good variables, how we will choose the best variable, and how we will discretize them in order to build the histograms or the distributions or the intervals. It is important to keep in mind that an individual, an object is not a two-thing in the object. An object is a different thing. An object you can describe by an infinity number of variables. You will never get the object. What people say on you is not you, if you want to summarize. So, how to improve quality of the symbolic data table, how to choose the best encoding of the initial classical variables, how to choose the symbolic variables that you will add, how is it to be done in order to optimize at least 4 kinds of names. The quality of the obtained distribution. So this is, as I said to some of you who asked me questions, the standard statistics is one cell of the symbolic data table. It is a cell where you, from a class, you define laws, and you find the parameters of the law, you infer the parameters of the law, you infer the model. So, we have this problem in symbolic data analysis to choose a good model. So, to choose a good model, there exist big, Cretan, Indian, AIC, MMM, like, or other criterion of this kind based on the likelihood estimation. So, if you want to have good distribution in each cell, you can use this criterion. Now, the second thing that you can optimize is the level of discrimination between the obtained symbolic description. It can be measured by the sum of the dissimilarity 2 by 2. So I say that when I calculate the similarity 2 2 between symbolic objects, what does it mean? What is the similarity between this row and this row? How can we measure that? How do we measure the similarity between two histograms? For instance, you can see that these two, also the better, are closer than these two. The first and the second are closer than the first and the third. So how do you calculate the similarity? For instance, the only way to do that, you can calculate the difference of these values, this and this, the difference of this and this, calculate the absolute value of the difference, and make the sum. You keep the idea? To calculate the dissimilarity, you just calculate the difference between this value. Maybe this is 0.8, 0.9, 0.9 minus 0.8 is 0.1, plus this 0.3, the difference is 0.3 for instance, so 0.1 plus 0.3. So you have the dissimilarity. And our aim is not to choose variable where all the histograms are the same, but to choose the variable where the dissimilarity will be not small but high. You want that the things will be as different as possible. If not, you don't give any information. Okay? No? Yes, if I have the same thing everywhere, general is not a good variable. I don't know anything about that. This will not explain what is the difference between the regions. So, this first was about the quality of the distribution. If we replace the histogram by a law, the histogram converge vers law, so the law will be good, more or less good, and you can mathematically to know how much it's good or not. The component is the distance, the dissimilarity, 2 by 2. The third point is the higher level of correlation between the bees associated to the different variables, what are called metamins. So this is here. I wish to find the categories here, and the variable, which categories gives a correlation between the variable name, for instance, and the variable GD of insecurity, and you wish that they have the best, the maximum correlation. If you have no correlation, it's not so interesting. So, for instance, to do a PCA, you will have a good correlation circle, so you have a good PCA. The more the variables are correlated, the better will be the PCA. The more clear will be the points. You will be better the difference between the different regions. So here, you have put the mean, the GD, the yes, here the rule, full, no, and this is the remaining part. And so I want that this thing be as correlated as possible. So this is the second condition. If you want to improve your symbolic table. The third one, correlation. The fourth one is someone has asked me, a girl has asked me about the entropy. What is entropy? She said. So I told her, why you didn't ask the question before? She said, because my English is so bad, I don't want to have enough of me. But it was a good question. Why entropy is important to get information from a single data table. In fact, as I said before, entropy is viewed in physics because they say that generally a system goes always for the maximum entropy. For instance, if you have something very hot and something very cold, you put them together, the entropy will increase until you have the same temperature in both. So here is the same question. If you have the same frequency for women and for men, here, half-half, this is not very interesting. This is just the same thing. But if you have a region where you have only men or only women, this is interesting information. And in this case, the entropy goes towards zero. When you have, this is the contrary of the increasing, this is decreasing. So we need to find cells which minimize the entropy. And so you can do it also for intervals. If you have an interval which covers all the people, all the values, this is not very interesting. If you have a very short interval, so this is an information. And you can express this in terms of entropy. So in that way you obtain an explanatory single data table, which is very important. And then when you get good variable, good discretization, because discretization here, what I call discretization. Discretization is how to cut the variable. Here we have only categorical variable, but maybe as an example here we have what does it mean? I don't remember. But if you have age, for instance, if you have the age is a continuous variable. The question is how to cut the variable age in order to have a good histogram. If you cut it bad, for instance, what I mean by cut, I take 1 to 5 years old, 5 to 10, 10 to 15, 15 to 22, and so on. And if you cut in a good way, you will have good discrimination between the histograms for each class, for each concept. But if you choose badly the discretization points, you can have the same frequency everywhere for each interval. And so in that case you don't give any information. So it's important to choose the best. And we have developed, there's mathematical behind this because it is an optimization problem. We have developed methods to find the optimal solution which gives you the best discriminating power between the histograms. There is an algorithm which does that, and it is in the software. So when you give a continuous variable, you can obtain the best discretization in terms of maximizing the dissimilarity between the histograms in the simulated data table. So the first field where much research has to be done is to improve the explanatory power of a single data table. Also, when you have find the best variable, I have shown you before that you can sort them in order to have the first variable, the best variable at the beginning. Now, much needs to be done to extend to some graphical visualization of similar data. You have asked me a question about correlation, so many ways to do that has been done, much has to be done. Some people make some assumptions that people doesn't like, and so on. The similarity between symbolic description can find out the similarity between symbolic description and use near symbol methodology in symbolic data analysis, extended clustering, canonical mapping, decision tree, PCA, canonical analysis, Bayesian tree, multi-level analysis. Maybe if you know multi-level analysis, I can explain you what it is and how we can extend that. Variance analysis, vector supermachine, mixture decomposition, multi-level analysis, learning machine by groups, etc. I think you know this technology, no? No. This standard method that we teach in data mining. So extend all this stuff to single data, to be done, and much has to be done. Now, when you have developed a single data method, for instance the PCA, you have to, if you want to do some theory, you have to go further. You can try to prove this fourth theorem. Suppose MNK is supposed to be a single data analysis method, where K is the number of classes obtained on n initial individuals. So the ground level of units are individuals. N individuals. The number of groups of classes are K. K is the number of classes. Theorem 1, if the K classes are fixed and samples in each class tends toward infinity, then M and K converge toward a stable position. If your method is good, it's really nice to have this result. Second one, if K increases in getting a single individual by class, then M and K converges toward the standard method. I think Valdemar says that this morning. So M and K is a symbolic method that presents in K parameters, n number of individuals, K number of groups. Theorem 3, if K and N increase simultaneously towards infinity, then M and K converge toward a stable position. And finally, the last theorem, which is the most important for a statistician, if the K laws associated to the K classes are considered as a sample of a law of laws, you see you have a column. So a column of histograms, for instance. You have K rows, K histograms. Each histogram is associated to a law. So you build this histogram by sample for each class. So then MNK applied to this sample converge to MNK applied to this law. The law of law converge when each law converge, if you want, in other words. I repeat, if the K laws associated to the K classes are considered as a sample of laws, this is the law of all the histograms, then MNK applied to this sample, converge to MNK applied to this law. Now, from lower level of individual observation to a higher level observation of classes, higher level models are needed. So here I have the standard data. This is the standard data on which you are used to work in statistics. Here is the age of Messi. And here I have the histogram of the age of the Messi team. Because here I have the teams. XG is a standard random numerical variable with numerical values. X prime G is a random variable with histogram values. Question: if the law of Xj is given, what is the law of X prime J? So what is the law of distribution? What the law of distribution laws? So what is the law of law, if you want? What's the law of law? So Dirichlet models can be used for that. Dirichlet has think about that much before big data and complex data and so on. He has made a nice work that you can use, that you have used for that. Now, if you, by using big and so on, you find the parameter of a law in a cell. With standard statistics, we know very well how to do that. You maximize the likelihood and so on, and you find the parameters. For instance, quotient law, you have mu and sigma. You know how to do that. But you can do this for all the cells. So the question is find having the parameters, so in each cell you have now parameters. Find the law of the parameters, find the law of the mean. Find the law of the means. You have a mean here. You have a mean for the team of Costa Rica, you have here the mean of the team of Brazil and so on. What is the law of this mean? Find the law of the parameters for each single variable J, and the law of the asymptotic vector of parameter law. So, having this law, you can look what is the law of this thing. Example, if F is the density of the parameters of the uniform law of intervals, and G is the law of intervals, then we have this, we find this law. We have this property. I have a paper on that. Now, another thing which surprisingly appear very useful in single data analysis is the copula theory. Copula theory has been invented, found in the 1940s by Escuela. And in the single data analysis is a very natural idea. If you have one histogram for the Messi team here, of the age and the weight, for instance, and you have for this interval of age, we have this frequency, and for this interval of weight, we have this frequency. Now, what will be the frequency here? This is the probability of falling in this interval. This is the probability of falling in that interval. What is the probability, the joint probability of falling for x1 in this interval and for x2 falling in this interval? What is the joint probability? What is the joint probability of this and this? If I have 0.8 here and 0.2 here, what will be the probability here? Yes, this is under the hypothesis of independency. And this is the idea of copula. the SCLAR says this is not always the case. Sometimes you have not independency. So what is the role of the joint probability knowing the marginal? Because in fact, and he says that, but in simulated analysis you have marginals. And you can add the correlation, I explained with that already, but you have the marginals. So we need to find the joint if you want to compare these two variables. So, copula needing in simulated data analysis, copula express the link between the joint and the marginal. So you have here the joint probability, and here you have the marginals, and copula is the link between both. In case of independency, you make just a product. And the product is a copula. It's a special kind of copula. For example, if the probability that gender equal male equal you, then the security to have GD, the probability is V. If there is independency, the probability of having gender equal M and insecurity equal GD is U product by V. You know, this is known. In case, under the hypothesis of independency, marginally, in case of not, if you have not independency, you can use the copula family. The probability of gender equal M and security equal GD is a copula which depends on U and V, denoted like that. It depends of some parameters. By choosing the copula family, we have this kind of formula. This is a Frank copula family, but there are many other. Then, now, how can you know if this is a good copula for what you want to do? How can you measure the quality of the model in that case? So, find the copula which minimizes. If you want to know if it is a good copula, you have to find the copula which minimizes the difference with the joint. The difference between what you give and the real joint is low, you have a good model. You have just to calculate that. In order to avoid the restriction to independency hypothesis and to reduce the cost of this joint computing, you can compute the joint on the data, but if you have huge, big data, this is very hard. It will take much time. But if you have the model, you have just to make the product. To use the model, or make the product if you have independency. In that way, you can obtain a copular PCA, or copular regression, copular canonic analysis. So all this, as far as I know, has not been done. This is each copular method has to be done. So it's a thesis, it's a dissertation subject. Each of my slides here can give dissertation subject. And now I have other case is a case when you have a clustering method. Maybe you get some teaching on clustering. For instance. Here is a hierarchical clustering. Not know if they have course on that. Okay. So maybe you know that there is a bijection, one-to-one correspondence between hierarchies and ultrametrics. So in this case, you can calculate the difference between the ultrametric and the initial dissimilarity. And so by minimizing this distance, you can get the best hierarchy. But now you will ask me, but where are symbolic data here? The symbolic data are the number of each cluster. Here you have a cluster, you have a class, you can aggregate and you have symbolic data. But the question is, if you have the symbolic data here, and so if I have intervals, min-max intervals, which describe this cluster, the question is, are you sure that all the people whose value are in these intervals are here? Here. Where is it? Here. Are here. So if I say age here between 20 and 25, I'm not sure that all people have an age between 20 and 25 are here. I'm not sure. So, in symbolic data analysis, we build hierarchies in such a way that each level satisfies this property, which are called in Galois lattices concepts. In Galois lattices, a concept is a class such that defined by an intent. The intent are the intervals, the description, and the extent are the people which satisfy the intent. In that case, the intent is the age between 20 and 25. The extent is all the people which have age between 20 and 25. So all the stuff in symbolic data analysis in clustering is to find levels which satisfy this property. Now maybe you teach pyramids, no? Yeah. So maybe some of you had some teaching about pyramids. Pyramids are an extension of hierarchies which allow you to have overlapping clusters. And then instead of being in one-to-one correspondence with intrametric, you are in one-to-one correspondence with Robinson similarity. So this is another story. Robinson similarity has some properties that I can develop if you want, if you have time, if you ask me. So we have the same problem. We want to build a symbolic data table, a symbolic pyramid by having this property of concept, intent and extent must be satisfy both the property. The intent have an extent, which intent has an extent, which intent is the same intent is the first intent. You understand? If I have people between 20 and 25 years old, all these people who are here, their intent must satisfy this property to be between 20 and 25. Which is not always the case. Because the intent can be shorter. 3D spatial pyramid, you can also, all that people do in genoma and so on is to build hierarchies and find order here. In one linear, there's obtain a linear position of the points. Here you have the, if you do a hierarchy on the players, you have the players here, and you have the cluster of players here. If you do hierarchy on the teams, you have here the teams, and you have clusters of teams which are represented by symbolic data, which is the property I told you. But here, if two clusters intersect, necessarily one is included in the other. Where is the target? Oh. So the target has disappeared. If here if these two clusters doesn't intersect, so one is included in the other. But here, these two clusters intersect here, but one is not included in the other. So you obtain overlapping clusters, and this thing is in one-to-one correspondence with that. And if you want to optimize it, you have to minimize something like that with R. D minus R must be as close as possible. So D is the initial dissimilarity between the initial points or objects. And here the same. You can build, instead of having a linear result, you can have here a network. You build your hierarchy or your pyramid on a network, and you have in that case a one-to-one correspondence with Ardidian dissimilarities, and you want to minimize the thing. And also here you have symbolic objects in each level, and which must satisfy the conceptual lattice property I told you before. So there are many people who have worked on these things. If you are interested, there are much to do also in this direction. So much to do in building symbolic data from complex and big data. Much to do in multi-level analysis, which is another theory. Multi-level analysis theory is to you have a standard data table where some variables are different classes. So we have some variables which are at a higher level, at a different level. So the multi-level analysis is to study the influence of these class variables on the regression that they are looking for. What is the influence? So how can you apply symbolic data analysis in multi-level analysis? For instance, to look at the classes involved by the higher level or the class variable, and so you will have information. Also, you can extend multi-level analysis to symbolic data table. Because the aim is measuring the influence of the class variable in regression between the classical variables. Bayesian tree or network, you have here to define conditional probability between symbolic variables. We know how to do that, and papers are on the way. Contingency data table analysis. I think you had some teaching on contingency data tables. For instance, you teach correspondence analysis, or you have chi-square distances or chi-square tests, and so on. But what is the difference between standard contingency data table and symbolic data table? You see, here you have a contingency data table. If you take only one column, you have a contingency data table. So you have what you can do on one contingency data table, you have to extend it to several contingency data tables because you have several. So the question is how to extend what we know on one contingency data table to several contingency data tables. What is the correspondence analysis of such kind of thing, for instance? Functional analysis. In functional analysis, mainly the work is you have one variable whose value are functions, and they look this kind of table. So mainly one column of the symbolic. Mainly it's one column of the symbolic data table. So we can extend this works on functional data analysis to symbolic data. Mixture decomposition also, you know what is mixture decomposition? Is when you have only one data table, you can look if this data for one variable or for several variables follow Gaussian law. But in fact, it is generally false. In fact, you have a mixture of laws. So you have to find a mixture, which means you have to find several laws associated to classes of your data. And so this also can be extended to symbolic data. So I want to finish with a nice example that we have done not far away last year, and it is published in ADAC review, I think. It's about trachoma. Trachoma is an illness which renders children blind, due to some comment on dit, mouches, flies, due to flies. So trachoma caused by repeated ocular infection with the chlamydia trachomatis, whose vector is a fly, is an important cause of blindness in the world. This study was conducted in Mali. The first aim was to choose among 3 antibiotic strategies those with the best cost-effectiveness ratio. The second aim was to find the demographic and environmental parameters on which we could try to intervene. So we have studied many symbolic data tables, but the one who was very interesting was the following. We have taken these classes, or concept if you want, or category, the class 00, 01, 10, and 11. So 00 means the child had the illness before, and not the illness, and not the illness after they apply the strategy. He has not, he has, he has not, after, he has, and he has after, before and he has after. So the degradation is 0 before, healthy, and 1 after, ill. 0 means healthy, 1 means ill. Beginning, end. One of the 1 year study. It was 1 year study. These classes are directly issued from the given data and not from a clustering process. So you have 0, 0, 0, 1, 0, and 1, 1. And so we had many variables. For instance, the variable strategy, we could see that the third strategy here, it is décalage. This was here, 0, in the old class 01, yes, here. This is a class 01. The third strategy is the most frequent. So, we could say very quickly, the third strategy is the worst, stop it. Strategy is the most frequent in the worst class 01. Nevertheless, we cannot conclude that it is the worst strategy, as the degradation can come from the environmental variable of this class 01. What means the environmental variables? We have many other variables. There is a number of cows in the village, a number of other kind of animals, birds and so on. There is a new en Spanish? Et puis, Pozo? Pozo. Pozo, if the village has Pozo or not. So, is that? No, how do you say it? Well. Okay, well. So, hole with water. So all this environmental condition was important. And this environmental condition was not the same for each class that we have here. You can see the value are not the same. So the question was, does the fact that the strategy 3 is the most frequent error come from the fact that you have 0, 1, or does it come from the environmental conditions? So we couldn't conclude. So, how to conclude something? The idea is simple. We had to look in same conditioning environment, in same environmental conditions, if the strategy 3 is worse or not. So we have done that. We have seen that the third strategy remains the worst in 3 homogeneous environmental conditions obtained by clustering. Understand? Now we can conclude. Before we couldn't. So we have to think before deciding anything, even in simple data analysis. So here, the PCA, principal component analysis of the simple data table of degradation, could show you that here 0, 0 class is here, 0, 1, 0 is here, 1, 1 is here, and 0, 1 is here, and the 0 is here, and you could see very quickly this information. So here you represent, the PCA is done on all the variable, but you represent one variable which is a strategy, and you can see that. You can also represent another variable, the borehole well, this is named the borehole well, and you could see that the 0, 1 is when there is no borehole hell, mostly. And you could build the correlation circle and see where the strategy 3 it has some links with the borehole well and so on, and the other variables. So finally, to summarize, the SDA strategy was characterized by these two things. The classes are generally not obtained from a clustering process. The classes 0, 0, 0, 1 of degradation are directly issued from the given data. This is typically a case where you work on the data which interests the user, and not on clusters that you have found like that. But so this is really the data that the classes appear very naturally. Second point, the clustering strategy in SDA is not much used to build the classes to be studied. Well, this at the beginning I thought that, but in fact not. The classes are given usually by the users. It is mainly used in order to show dependencies or independencies between groups of symbolic variables. Here it was the case of environmental conditions. So, as a conclusion, the symbolic data analysis enhanced standard data mining and statistics by allowing this domain to work on complementary data table. It can enhance the domain of research like functional data analysis, multivariate statistic phase sets, rough set and granular computing. If you want, I can develop on that. If you ask me what is how simulated analysis can be positioned in comparison with fuzzy set, rough set, and granular computing, or multi-level statistics. Simulator have to be built from given standard complex data. They are not given, usually. Simulated data cannot be reduced to standard data. Okay, I hope I have shown that. Complex data can be simplified in simulated data. Big databases can be reduced in simulated data. Simulated data are the number of the future. So, thank you.
Gracias. Ahora damos algún espacio para preguntas. Todavía tenemos un poquito de tiempo. ¿Preguntas o comentarios?
Ask question even if your English is not very good.
Sí, pueden hacerla en español y nosotros le traducimos.
In the pyramid, when you show the pyramid, the case of the hierarchy, it's clear that the upper level contains all the individuals that are in the lower level, but in the pyramid that is not clear because the upper level contains only x5, but x3 and x4 also are contained in some other level. So the class should be with some degree of membership? Or?
No. The class is the class. The class contains the people that it contains. This class contains, this class contains 1, 2, 3, 4. And this class contains 3, 4, 5. Exactly. But some are in the bus.
There is an intersection.
Yes, there's an intersection. But the clusters are exact clusters.
Okay. Thank you.
Gracias. ¿Alguien más? I think everything is clear.
I doubt.
Ok, un último aplauso para el profesor.